Hi, I'm Andre Cruz. I'm a PhD student at Max Planck in Germany. And today we're here presenting at NeurIPS work of ours on the calibration of language models. And I guess the main point of the paper is we're trying to point out this blind spot in the literature, in the benchmarking literature in LLMs, that it's somewhat well known that LLMs-based models are very well calibrated on realizable tasks, or very well calibrated on benchmarks and multiple choice Q&A in general, like MMLU and all these sorts of benchmarks. We're pointing out that they're not actually very well calibrated on all benchmarks. They're just very well calibrated on realizable benchmarks. That is, usually factual benchmarks of what's the capital of France or what's the boiling point of water kind of questions. If you actually introduce data uncertainty in the benchmarks, then base models and instructional models alike tend to actually be very miscalibrated. So here on the left, we actually see that on MMLU type of benchmarks, this is GPT-4 before instruction tuning. It's super well calibrated. On the quality benchmark, which is other kinds of like factual, no uncertainty benchmarks, it's super well calibrated. But on unrealizable tests where there is some uncertainty in the data, like is it going to rain tomorrow? Or what's the weather like tomorrow? A, rainy, B, cloudy, C, sunny, then it's going to have actually very poor calibration. So we're pointing out this blind spot. And to show this, we actually just create a bunch of benchmark tests based on US census data. We create unrealizable tests, that is, we take US census data and we just try to predict one column out of a bunch of demographic features, for example, income prediction out of occupation, marital status, location, etc. And of course, this is unrealizable because it's not going to be a single answer. Different people that are described by the same features have different labels associated to them. And we use these tasks to evaluate calibration of language models, and then we conclude that actually base models and instructional models alike are very miscalibrated on these kinds of unrealizable tasks. One thing that we're pointing out is that the way that they're miscalibrated is very different from base models to instructional models. So base models tend to be very uncertain, and instructional models tend to be very certain, very overconfident. So base models are underconfident and instructional models overconfident. And we see this in the log odds because instruction-tuned models tend to have very spiky distributions, very polarized distributions of the output. So either 1 or 0 probability of A, B, C, D, whatever the answer is. And base models, the opposite. Base models tend to always associate 60% probability of A, 40% probability of B, or somewhere in between. So even though the failure of calibration is very different, the failure modes of calibration are very different, both are very miscalibrated actually. Yeah. One potential solution that we find is that actually if you prompt it instead of multiple choice Q&A, if you prompt it with what's the probability that this person earns an income above 50K, or what's the probability of something, if you prompt it in this certain way, of like a verbalized numeric prompt, calibration tends to actually be much better. So this is kind of the results that we show here. So left is multiple choice, right is numeric, and closer to the diagonal, the best. And multiple choice Q&A tends to be very miscalibrated, and numeric prompting is considerably better. So not perfect, but considerably better with respect versus multiple choice Q&A kind of prompting.